Hello, welcome to the first episode of the Pythagorean Theorem. We are not going to explain what the Pythagorean Theorem is, nor we're going to prove it. Actually, we will focus on a more than 100 years old incorrect claim. Then we prove it in different ways. In other words, we prove the Pythagorean theorem, showing that the claim is actually incorrect. What will be discussed later? There is a more than 100 years old incorrect claim by Loomis in his well-known book, The Pythagorean Proposition. In his book, Loomis claimed that there are no trigonometric proofs because all fundamental formulae of trigonometry are themselves based on the truth of the Pythagorean theorem. As a result, we cannot prove the Pythagorean theorem by means of trigonometry. Because if we do that, in the mind of Loomis, this is a circular reasoning. However, in this lecture, we will prove that the angle sum and angle difference identities are independent of the Pythagorean theorem, and the identity sine squared plus cosine squared equals 1. Actually, we could use the angle sum and angle difference identities to prove this. Notice here there is no circular reasoning because we are able to establish the angle sum and angle difference identities without using this identity. Therefore, we are able to show that the angle sum and angle difference identities can imply the identity sine squared plus cosine squared equals 1. Now, if this is known, then the Pythagorean theorem follows fairly easily. Sine squared plus cosine squared equals 1 is usually referred to as the Pythagorean identity because it looks like a Pythagorean theorem, and from the definition of sine and cosine, the validity of this identity is based on the Pythagorean theorem. So in what follows, we frequently use Pythagorean identity to refer to this identity. In early 2023, Ms. Jackson and Ms. Johnson presented impossible proof of the Pythagorean theorem at the AMS Spring Southeastern Sectional Meeting. AMS is American Mathematical Society, a very, very well-known society in the world. Why Jackson and Johnson would refer to impossible proof? Why is it impossible? It is because Jackson and Johnson used trigonometry to prove the Pythagorean theorem. The impossibility claim was due to Loomis in his very well-known book. This is the book by Loomis. The book title is The Pythagorean Proposition, in which Loomis collected 256 proofs in this book. The first edition of this book was published in 1907. And then this book was reprinted in 1940. And in 1968, the National Council of Teachers of Mathematics reprinted the 1940 version, which is this one. You may be able to find a PDF file for this book, which is a scanned PDF. This gentleman is Elisha Loomis. This photo was taken in 1935. This is a paragraph, or actually a section in Loomis' book. The title of this section is No Trigonometric Proofs. Why? This is because all the fundamental formulae of trigonometry are themselves based upon the truth of the Pythagorean theorem. Because of this theorem, we say sine squared plus cosine squared equals 1. As a result, trigonometry is because the Pythagorean theorem is. Today we know this is wrong. In what follows, we shall show that Loomis' claim that trigonometry is because Pythagorean theorem is false. I saw the paper by Dr. Jason Zimba. In his paper, Dr. Zimba proved that the angle difference formulas are independent of the Pythagorean theorem. That is the validity of psi of alpha minus beta and cosine of alpha minus beta does not relate on the Pythagorean theorem and the Pythagorean identity. That is the sine squared plus cosine squared being 1. In fact, the angle sum identity, sine of alpha plus beta, and the cosine of alpha plus beta can also be derived in the same way without the use of the Pythagorean theorem. Because the double angle identity can be used to prove the Pythagorean identity. Double angle identity comes from the angle sum identity. Therefore, from angle difference and angle sum formula, we are able to prove the Pythagorean identity. As a result, Loomis' claim is false, because the Pythagorean identity can be proved without the use of the Pythagorean theorem. So the detail goes as follows. The angle difference identities do not depend on the Pythagorean theorem and identity due to Dr. Jason Zimba. The angle sum identities do not depend on the Pythagorean theorem and identity. We will prove this. As a result, the double angle identities are also independent of the Pythagorean theorem and identity. With the help from calculus and L'Hopital rule, we can derive the Pythagorean identity and hence the Pythagorean theorem using the double angle identity. Actually, we can do more. We will show you at the end of this lecture. The first question are the sine of alpha minus beta and the cosine of alpha minus beta independent of the Pythagorean theorem and the Pythagorean identity? Answer, yes. We will follow Dr. Zimba's proof here. Because we are dealing with right triangles, we shall assume that the three angles are 90 degrees, the largest one, is larger than the second largest one, alpha, which is larger than or equal to the smallest angle, beta. Now, here's the proof. Remember, we assume 90 degrees is greater than alpha, which is greater than or equal to beta. This diagram shows you all needed. Now, line OP makes an angle of alpha with the x-axis. Line OQ makes an angle beta with line OP. Therefore, the angle between OQ and the x-axis is alpha minus beta. Furthermore, we assume that the length of OQ is 1. Now, drop a perpendicular from Q to line OP, meeting the line OP at P. Therefore, OPQ is a right triangle with angle P being 90 degrees. If you are interested in Dr. Zimba's proof, you may be able to find a PDF copy here. Now, let's analyze a few triangles, then the result is obvious. First of all, let's drop perpendiculars to the x-axis from P and Q, meeting the x-axis at S and T. We also drop a perpendicular from Q to the line PS, meeting PS at R. Therefore, this is a right triangle, this is a rectangle. Now look at triangle OQT. This is a right triangle because the hypotenuse is 1. And the angle here is alpha minus beta. So QT is sine of alpha minus beta. OT is cosine of alpha minus beta. QT, OT, we know the length of these two. What we're going to do is find the length this one, this one, this one, and this one. Now look at triangle OQP. This is a right triangle by construction. Angle P is 90 degrees. Because the hypotenuse is 1, so PQ is sine beta, because this angle is beta. OP is cosine beta. We have it here. Then the third triangle we're going to look at is triangle OSP. And this is a right triangle because this is a line perpendicular to the x-axis. The angle here is alpha. So PS over cosine beta is sine alpha. By the same reason, OS over cosine beta is cosine alpha. So we have this here. So OS is equal to cosine alpha times cosine beta. SP is equal to sine alpha times cosine beta. Now, look at this smaller triangle, PQR. This is a right triangle. Angle P here is alpha. This is a simple exercise for you to do. So in this right triangle, this side, the hypotenuse is sine beta. We obtained it earlier. Therefore, cosine alpha is equal to PR over PQ, which is PR over sine beta. Therefore, PR is cosine alpha times sine beta. By the same reason, the length of RQ is equal to sine alpha times sine beta. We are almost done. Let's copy everything from the previous 4 slides here. Sine of alpha minus beta is here, QT, which is equal to PS minus PR. Cosine of alpha minus beta is OT, which is the sum of OS and the ST. Now we know OS, PS, PR, RQ. Plugging this value into here and here, we have sine alpha minus beta equals this. And also we get cosine. As a result, we never use the Pythagorean theorem nor the Pythagorean identity to prove this one and this one. Therefore, the angle difference identities are independent of the Pythagorean theorem and the Pythagorean identity. Now, let's prove the Pythagorean identity. Cosine 0 is 1. 0 is equal to alpha minus alpha. So, according to angle difference identity, alpha here, alpha here, alpha here, and alpha here, we have cosine squared plus sine squared. In this way, we prove the Pythagorean identity. Therefore, Loomis' claim is false. This is our first result. Then let's move to the second question. Are the angle sum identities independent of the Pythagorean theorem and the Pythagorean identity? Well, the answer is certainly a yes. The proving technique is the same as what Dr. Zimba used. So let's prove angle sum identities. The diagram here is nearly identical to the one used in Dr. Zimba's proof. Again, we assume that alpha plus beta is less than 90 degrees. If alpha plus beta is equal to 90 degrees, well, the proof is easier. Let me leave it as an exercise. Now, the construction goes as follows. Line OP makes an angle of alpha plus beta with the x-axis. Line OQ makes an angle of alpha with the x-axis. Therefore, the angle between OP and OQ is beta. We assume that the length of OP is 1. From P, drop a perpendicular to the line OQ, meeting it at Q. Therefore, OPQ is a right triangle with angle Q being 90 degrees. First of all, let's look at the right triangle OPQ. Remember, Q is the perpendicular foot from P to OQ. Because OP is 1, this side PQ is sine beta because the angle beta is here. And the OQ is cosine beta. Now look at triangle OPS. Remember, OP is 1. Therefore, PS is sine alpha plus beta. OS is cosine of alpha plus beta. Here, in triangle OQT, this is a right triangle here. Now the angle here is alpha. So QT over cosine beta is sine alpha. Therefore, QT is sine alpha times cosine beta. For OT, we have cosine alpha, cosine beta. So we are almost done here. The remaining is this triangle. Look at this triangle. Again, this alpha is equal to this alpha exercise. So in this one, PQR, now PQ is sine alpha. So PR over PQ is cosine alpha. Therefore, PR is cosine alpha times sine beta. Now, RQ over PQ is sine alpha. Therefore, RQ is sine alpha times sine beta. RQ is equal to ST. So we are almost done. OT is equal to OS plus ST. And the OS is cosine alpha plus beta. And the ST is sine alpha cosine beta. Their sum is OT, which is cosine alpha cosine beta. So we have this. PS is equal to PR, which is cosine alpha sine beta, plus RS, which is sine alpha cosine beta. We have this. Therefore, the angle sum identities are also independent of this Pythagorean theorem and the Pythagorean identity. How about double angle identity? The double angle identity, we just use alpha beta equal to x. So we have 2x, we have this. Because the angle sum identities are independent of the Pythagorean theorem and the Pythagorean identity, the double angle identity, which are direct consequences of the angle sum identities, are also independent of the Pythagorean theorem and the Pythagorean identity. Can we prove this Pythagorean identity using the angle sum identities? The answer again is yes, but a little bit complex. What we need is the following. We need to prove that the derivative computation of sine and cosine are independent of the Pythagorean theorem and the Pythagorean identity. To compute the derivative of sine, we need a product to sum identity. We also need to compute the limit of sine x over x as x approaches 0, being 1. This computation is also independent of the Pythagorean theorem and the Pythagorean identity. Check your calculus book. It's obvious that the computation of this limit is independent of Pythagorean theorem and the Pythagorean identity. The remaining is easy. So what is the product to sum identities? From angle sum identities, we have this and this. Now subtract the second one from the first one, we have this. That is sine of alpha plus beta minus sine of alpha minus beta is equal to 2 times cosine alpha and sine beta. So this part is the product, and this part is the sum. So this is referred to the product to sum identity. We only need this one. Let's say P equals alpha plus beta, and Q equals alpha minus beta. Plug in P here, Q here. According to the product to sum identity, we know sine P minus sine Q is equal to 2 cosine of P plus Q over 2 times sine of P minus Q over 2. This is what we need for the derivative computation of sine x. Okay, here is the computation. The derivative of sine x is defined to be sine x plus h minus sine x over h, where h is a small value, and the derivative of sine of x is the limit value when h approaches 0. According to the product to sum, the numerator becomes this: 2 cosine P plus Q over 2 times sine of P minus Q over 2. This term becomes cosine of 2x plus h over 2. This one becomes x minus x. They canceled out, only h remaining. So h over 2. Then we pull 2 to the denominator, so it becomes h over 2. Now, this one, when h approaches 0, is 1. Remember, we mentioned sine x over x. Its limit value when x approaches 0 is 1. And the computation of this term does not need the Pythagorean theorem nor the identity. For this term, when h approaches 0, this term goes to x. Therefore, the limit of this term is cosine x times 1, which is, of course, cosine x. In this way, we proved that the derivative of sine is cosine without using the Pythagorean theorem and the Pythagorean identity. For cosine, it's much easier. We only work on a right triangle is equal to sine of 90 degrees minus x. So the derivative of cosine is equal to the derivative of sine of 90 degrees minus x. According to the chain rule, to compute the derivative is derivative of cosine with this argument times the derivative of the arguments here. So cosine 90 degrees minus x is sine x. The derivative of this term is negative 1. This is typo, negative 1. Therefore, we have negative sine x. Therefore, the computation of the derivative of cosine x does not need the Pythagorean theorem and the identity. So, we have all the ingredients in hand. We are able to prove the Pythagorean identity without using Pythagorean theorem. Recall that these two are the double angle identities. So sine square and cosine square can be represented as follows. Sine square, we apply this as if it's 2 times x over 2. So we simply apply the double angle. We have this. This is sine 2 times x over 2. The square moves here, which is equal to 4 sine square of x over 2 times cosine square x over 2. For cosine square x, we make that 2 times x over 2. We have this. Now, we expand this one. We have cosine raised to the 4th power minus 2 times this term and this term, plus the square of this term. Therefore, sine square plus cosine square is the sum of these two. Now, this 4 times this and the negative 2 of this cancel out half of it, becomes sine square of x over 2 plus cosine square x over 2 square. So continue this, replacing this x over 2 by x over 2 square, we have this. And this is doubled. Continue this process. Eventually, for any n, you have this. Sine square plus cosine square is sine square of x over 2 raised to the nth power plus cosine square of x over 2 raised to the nth power, and the sum is raised to 2 raised to the nth power. Well, if you know this is obvious, because the sum of these two is 1, so all terms here are 1s. But we need to prove it. To prove it, we need some calculus. Recall that a raised to the b's power is equal to e raised to b times log a, where exp is the exponential function, and Ln is a natural logarithm function. Therefore, this formula, sine square of x over 2 raised to nth power blah 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 becomes this. We have a exponential here. The exponent b goes outside times log of this one. Now, we need a little bit trick again. We put this in the numerator. We move 1 over 2 raised to nth power to the denominator. Now that looks quite interesting. When n approaches infinity, this term goes to 0. When n reaches infinity, this term goes to 0, and the cosine squared goes to 1. For this term, when this term goes to 0, sine squared goes to 0. Therefore, when n goes to infinity, here we have 1. Here we have 0. But this one, after taking log, is 0. Therefore, when n goes to infinity, we have an exponential of 0 over 0 in definite form. Of course, we need the L'Hopital rule to compute the limit. Is it very difficult? No, not at all. For convenience, let's say h to be 1 over 2 raised to the nth power. So this term becomes x times h. This term is also x times h. And the denominator, 1 over 2 raised to nth power, is h. N approaches infinity, h goes to 0. So what we need to do is find the limit of this expression when h goes to 0. Now, L'Hopital rule says that when we have 0 over 0 in definite form, we could compute the derivative of this and the compute the derivative of this. And then the result is the same. And actually the one we want. Now, if we compute the derivative of this one, well, that is 1. Now, how about the top term? We copy this one here. We differentiate the denominator. That's log. It's equivalent to log x. So the x goes here. So then we differentiate this x. Now, 2 sine square square of xh is 2 sine xh times the derivative of sine, which is cosine xh, and then we differentiate xh, we have h. Now, doing this, we get here. Obviously, these two terms cancels out. So the denominator is 0, and the denominator is 1. So according to L'Hopital rule, when h goes to 0, the limit is 1. Therefore, sine squared plus cosine squared is 1. Let us do a little bit more. Because the derivative of sine and the derivative of cosine are independent of the Pythagorean theorem and the identity here, we can use this property to prove the Pythagorean identity. Let the function fx be sine squared plus cosine squared. Now, differentiate f like this. So f here, we differentiate here. Now, the derivative of sine squared is 2 sine cosine. The derivative of cosine squared is 2 cosine times minus sine, which is 0. What does that mean? It means fx is a constant. So we can assume that fx is equal to a constant c. What is this C? It's easy to figure out. You put 0 here, sine 0 is 0. Cosine 0 is 1. Therefore, immediately we have the function fx is 1. So, we proved the Pythagorean identity. Going from the very beginning to the very end up to here, we never use Pythagorean theorem nor Pythagorean identity to prove anything. Instead, we prove Pythagorean identity by using various techniques. So, here is a summary. Elisha Loomis published the book, The Pythagorean Proposition, in which 256 proofs are presented. Very interesting. If you are interested, there is a scanned PDF file available as indicated earlier. In his book, Loomis claimed that the Pythagorean theorem cannot be proved using trigonometry because the identity depends on Pythagorean theorem. This incorrect claim has been cited widely for more than 100 years. We prove that it is incorrect. When Miss Jackson and Miss Johnson present their impossible proof, this incident was reported by the media widely. Many media reports indicate that this is an impossible proof because of Loomis' claim. Now you know why Loomis' claim is incorrect and Loomis was wrong. We prove the following. The angle sum and angle difference identity are independent of the Pythagorean theorem and the Pythagorean identity. The derivatives of sine and cosine are also independent of the Pythagorean theorem and the Pythagorean identity. In fact, the Pythagorean theorem can be proved using the angle sum and angle difference and other mechanisms. Now, if we know the Pythagorean identity, you can easily prove the Pythagorean theorem. Here are the references. Elisha Loomis' book, The Pythagorean Proposition, 2nd edition. A scanned PDF file can be found here. Dr. Zimba's proof is presented in this paper. You may also be able to find a PDF. So let me stop here for this talk. Hope you'll come back next time for the next 2 episodes on the Pythagorean theorem. Goodbye and good luck. See you next time.